Assalamualaikum and a very good day. So the next application of an op-amp is differential amplifiers. Differential amplifiers are useful because it rejects common voltages while amplifying the differential signal of interest. For example, suppose we have equal 50 Hz noise that is present on each input, and one input is at 5 DC while the other is at 2 volt DC. So the circuit removes the noise and amplifies the 3 volt DC of the differential signals. So for the V out of the differential amplifiers, we have the expression of RF over R1, V1 minus V2. So how do we get this expression? Okay, let's see the first one. We focus on the first one is on the non-inverting terminals. So let's say we have here. Okay, so we know that the current that flows into the op-amp is equals to 0 because of the ideal op-amp. There's no current flows into the op-amp, so what's left is we have the voltage V1 that passing through the R1, and then it goes to RF and finally goes to the ground. So here we can use a voltage divider rule to get the expression of V plus here. Okay, so V plus is equals to RF over R1 plus RF multiplied by V1. Okay, and then we have the next characteristic of ideal op-amp. Both input sticks together, so meaning that we have V plus equals to V minus. Okay, this is the first one. This is the second one. Okay, so the third one we look at the next terminal, which is inverting terminals here. So what we have here is that again there is no current that flows into the op-amp, so I equals to 0. So we have here is a V minus. Okay, so we can come up with expressions. We have V2 minus V minus over R1 equals to V minus minus V out over RF. So how do we come up with this expression here? Number 3. So basically it's because of the KCL. Okay, remember here? So we have the current that go through R1 from V2, we call it is I R1, for example, and then the current that goes through RF is I RF. Since there is no current that goes through flows into the op-amp, so we can say that I R1 is equals to I RF. Okay, that is why we come up with expression number 3 here. Alright, so we make it more simpler in order for us to put the expression number 2 and number 1 into the expression of number 3. So now we have V2 minus V minus equals to R1 V minus minus R1 V out, and then we have RF over RF. So we put them together, we can have RF V2 minus RF V minus equals to R1 V minus minus R1 V out. Okay, so the next is RF V2 plus R1 V out equals to R1 V minus plus RF V minus. Okay, so we can group them together as R1 plus RF of a V minus. Okay, so what we have here is V minus. We have RF V2 plus R1 V out. So V minus is RF over R1 plus RF, okay, from the expression of number 1 and number 2. So we put here RF over R1 plus RF multiplied by R1 plus RF here, and don't forget to put the V1. Okay, so we can basically cancel this. So what we have now is we have RF V2 plus R1 V out equals to RF V1. Okay, so we want V out, so we have R1 V out equals to RF V1 minus RF V2. So V out equals to RF over R1 V1 minus V2. So we have proven that the voltage output of differential amplifiers is equals to RF over R1 V1 minus V2. See you again in the next video.